Okay, 4.2, we're going to look at the mean value theorem for derivatives. The mean value theorem for derivatives says that if our function is continuous over a closed interval from a to b and differentiable over the open interval from a to b, then at some point in between a and b, the derivative is equal to the slope of the line connecting the endpoints. F prime of c equals the slope of the line going from point A to point B. And notice that the mean value theorem only applies over a closed interval, so we have to look back up at those conditions there. It has to be continuous, differentiable, and closed. And so the big idea here we need to understand is that at some point in the closed interval, the actual slope at a point is equal to the average slope, or the slope of the line connecting the endpoints. So here we have some function going from a to b. Somewhere between a and b, there has to be a point on that curve where the tangent line has the same slope. And so somewhere right about there, the tangent is parallel to that chord. So there is some c between a and b where f prime of c is equal to the slope of the line connecting a and b. Okay, we need to define what we mean by increasing and decreasing. A function is increasing if when x1 is less than x2, then f of x sub 1 is less than f of x sub 2. So as we move from left to right, we have x sub 1 is less than x sub 2, the corresponding y value to x sub 1 is less than the corresponding y value to x sub 2. Decreasing if x sub 1 is less than x sub 2, and then we can reverse the inequality here. F of x sub 1 is greater than f of x sub 2. And it's really important that we understand that increasing does not mean that the derivative is positive. Decreasing does not mean that the derivative is negative. Now, if the derivative is positive, it is increasing, but we could also have the derivative equal to 0, at which point it could be increasing or decreasing. Take a look at this right here, y equals x cubed plus 1. When x equals 0, the derivative is 0, but this function is increasing because as we move from left to right, every y value is larger than the value that came before it. So even though we have a slope of 0 at one point, it's still increasing all the way over that interval. So increasing and decreasing refers to intervals, not to individual points. Look at negative x squared plus 2. This function is increasing from negative infinity to 0, and we can include the 0. Decreasing from 0 to infinity, again, we can include the 0. So 0 was included in both the intervals where it's increasing and decreasing, because in both cases it satisfies the conditions of our definition. Okay, now we're going to switch gears a little bit here. We have two functions, y equals f and y equals g. And these two functions have the same slope at every x value. G of x has just been shifted up c units. So these two functions would produce the same derivative. So let's take a look at a function, or actually let's find the function f of x, whose derivative is sine of x. So keeping in mind what we just saw on the previous page, we know that a function could produce sine of x, but could differ by some constant. So let's see, derivative of cosine is negative sine, which means the derivative of negative cosine is sine. So our function could be negative cosine of x, but it could vary by some constant c. So we would write that f of x equals negative cosine of x plus c. C could be 0, 1, 2, negative 3, could be any number potentially, because if we took the derivative of a constant, we'd get 0, and we would get our derivative of sine of x. Now we have this extra information that this graph passes through the point 0, 2. So plug 0 in for x, 2 in for y, and we find that c equals 3. So our function that gives us the derivative of sine of x and passes through the point 0, 2 is negative cosine of x plus 3. So if we're going to figure out what that constant was, we have to have this additional information, these initial values. So we give this a name. We're doing derivatives backwards. We call this the antiderivative or anti-differentiation. And we use capital F of x to denote the antiderivative of a function little f of x. So the derivative of capital F of x is lowercase f of x. Antiderivatives will be a really big part of this course. We're just looking at an introduction of how to find them, and we'll investigate them a lot more in the future. Okay, so we want to find velocity and position if we have downward acceleration of 9.8 meters per second squared. So this is a little bit different from anything we've done before. We've started with a position equation, and we have found velocity and acceleration. Now we're starting with our acceleration equation, and we're going to find velocity and position. So we're going to work backwards. Notice we have some initial conditions here. We know that our initial velocity is 1 meter per second, and the initial position is 0. So a of t is 9.8. We're going to let down be positive. So velocity is the antiderivative of acceleration. So the antiderivative would be 9.8 times t plus some constant c. But we know that the velocity is 1 at time 0, so we can plug those in to find c, and c equals 1. So our velocity is 9.8 t plus 1. Now to find position, take the antiderivative again. So we know that if we end up with a variable t, that would have been the derivative of t squared, or 1/2 t squared. So the antiderivative of 9.8t is 1/2 times 9.8t squared. The antiderivative of 1 is t. And in general, with antiderivatives, the best thing to do is try something. You might have those constants incorrect, but try something and then check by taking the derivative and make adjustments as necessary. So we can simplify that down. We know that the initial position is 0 at time 0, so plug those in for s and t, and our constant is 0. So our position equation is 4.9 t squared plus t.